doing fine. Hope my sound and video are okay. We have a long day today. I just want to mention that lately I'm putting the timestamps, okay, but I can put them only after YouTube uploads the video or whatever they do, render it. And so it usually takes until the next day, okay? But I do put the timestamps now, and I think that helps people, go over the stuff that they don't want to hear about and go directly to the stuff that they do want to hear about, okay? Anyways, I got a lot of fan mail, and I can't get to all of it, okay? So if I miss you, please don't hold it against me. I've got enough. I've got more than enough fan mail as it is, okay? So let's start with the first one, okay, here. And this is a couple first ones are of an administrative nature, okay? Is there really no way to interact with the RSM community, the Rational Scientific Method, without using Facebook? I think not. I think that group is only in Facebook. Maybe they're somewhere else. I don't know about it. As far as I know, all these folks are in on Facebook, and I have put it in the descriptions, the links, so you can just go there and if you're interested, and join in the fun. Okay, and they'll give you a run for your money, I'm sure. Okay. Sound is too low. Well, I got it at max. I don't know. I have no idea why the sound is low. Hello, hello. I don't know. I got it on max. What else can I look at here? I don't know what else to check. Everything here checks out okay. I don't know. Am I shouting too hard? I don't know. I have no idea. Everything here checks out okay. The sound. What else could it be? Okay. I don't know. Turn your volume up. I have no idea. I've checked everything here. My sound here is coming out okay on the meter. So what else can I check? Hello, hello. No, it's okay. I don't know. Well, I'll try to speak a little louder. That's all I can do. Maybe get a little closer. That's about all I can do. So let me continue here. If you want to get into the rational scientific method, you can just go in to Facebook. As far as I know, that's the only place where the group meets. Maybe there's some other place, but I'm not aware of it, okay? Second issue, important for me, this fella complains. He quotes me and says, I don't block, delete, or censor. He says, you censored me twice without explanation in September and on 1st of October 2014 when I commented about what is physics. I said it is about objects, la la la. Okay, you deleted my comments and you closed the comments section. Okay, so let me clarify that. First, I do concede that I deleted the comments and that I did close the comments section. Okay, so I swear to God, hope to die. Now let me tell you the important part. The important part is the context. Okay, that's what's the important part here, and that's that the reason I had to delete comments. Actually, I wanted to do something else, but it didn't work any way I did it. Was because people come in, they put comments, and they get into a discussion with me. They used to. This is in the old days. Again, he's talking about 2014, okay? And we would get into a discussion, long discussions with lots of people. I have more than 5,000 comments. I'm talking about lots of comments here. And what happened, these people would come later, some of them, right? And they would delete their comments. So instead of a dialogue, I ended up monologuing with a wall. Okay, they only left my comments. And so what I had to do was delete my comments. And because I had to delete my comments, I really had to delete all the comments because of these folks. Because otherwise people would say, hey, Bill, it looks like you're selectively deleting comments. So I had to delete all the comments. And that was a pain in the butt because YouTube doesn't have a function where you can delete all the comments at once. So I started deleting comments there, trying to get rid of all of them. And eventually I had to shut down and say, no, no, this is just too much work. And what I did was I simply disabled comments. Okay. And again, that was before starting the series here. So what's the solution? The solution why I'm saying I don't delete comments is that I don't answer comments anymore, not on YouTube. Okay. Anyone who wants to put a comment, no problem. I'm going to address it here. If I think it's interesting, important, or whatever, I want to address it. But I don't delete comments. The only time I deleted comments, not because of me, but because people left me talking in the air. Okay, they came back and they deleted comments. They did the same thing in the rational scientific method, and after a while they got the hang of that, and they would copy make a backup of all the comments made. So if people came in there and they deleted the comments, what the owners of the site did was they would go in there and just put the comments right back in because they had a copy of them. And so that's always a problem. What I do now, the new policy is I don't delete any comments. I never did, really. This was not because of me, it's because of what these people did. And so I don't delete comments. What I do now is just don't answer them on YouTube. I'd rather answer them here. I think it's more practical. Okay, and that way I don't get left dangling out there in the air talking to the wall. Okay, so that was the issue. Okay, so I apologize if I deleted your comment, but I want you to know the reason. And that was a way back then, several years ago. The other issue is I didn't delete your comments specifically. I deleted a whole bunch of comments. It's not like I targeted you or anything of that nature. Okay, I want you to understand that. But yeah, I do apologize. There's nothing I can do about it. I had to delete all these comments. What I did now is a lot of the comments are still there, but I just disabled comments on the old videos, on the ones where I entered into discussions with people. People couldn't take it and they did nasty things. Okay, let's get on with some more comments here. It says, you say that there's only theoretical physics and that is physics. Everything else is not science, and that is perfectly reasonable, okay? Wouldn't this mean that science is completely limited to physics hypothesis only, okay? After all, there is no such thing as theoretical biology, okay? What name do you propose for practical disciplines currently known as science, such as biology, meteorology, etc.? Technology is about gadgets and such, but what about medicine, virology, and those kinds of studies? Is there no blanket term, and they all must be referred to by their specific line of study? The issue is that, science, we define science as rational explanations. If it's not an explanation, it's got nothing to do with science. Okay, so we're looking for explanations, specifically mechanisms. So if you have a mechanism, you propose a mechanism for how Mother Nature runs her shop, hey, we're interested in hearing it because we think it's part of science. Now, what's happening? People confuse technology with science, okay? And so what happens? They go out there and they say, well, medicine, this guy's fixing a body, operating or whatever. Well, that's technology. That's not really science, okay? Science is explaining how you cure someone or why you cured them, why that person got cured. That would be science. That would be the branch of science within the branch of medicine, okay? But if you just go in there and you're a handyman, you work with your hands, and you're a doctor and you cure someone, you didn't do any science. You didn't do any science. The fact that you cured them is like developing a gadget at a factory. You're not doing science. And again, also mathematics is not science, has nothing to do with science. If I describe a chair mathematically, of course, four legs, backrest, a seat, did I do science just because I described it mathematically? Repeatable because I get another chair, describe it just the same with the same equation. Is that what science is about, just describing? No, that's nonsense. That's what Rutherford said is just stamp collecting. There's physics and stamp collecting. Physics is explanation, and he didn't understand that either. Okay, just so you know where I'm coming from on this. Okay, another comment here. Moving on. Molecule, group of two or more atoms that form the smallest identifiable unit into which a pure substance can be divided and still retain its composition and chemical properties of that substance. Oxygen molecule O2. Water molecule H2O. Air molecule doesn't exist. Okay, yeah. Just want to say that we usually identify O2 with air. Okay, so when I say air molecule, I'm referring to the oxygen molecule. That's all there is to that. It's just a matter of that is a semantic issue, a strictly semantic issue. When I say oxygen or when I say air molecule, I'm referring to the O2 molecule. There are trace elements in air, okay, and I'm not going to mention all of them. You got zinc maybe floating in there. Who knows what else? And depends on the place on the planet where you're at. If you're in New York City, you can cut the air, with a knife. Got smog and all that stuff. In fact, if you look at it here, I've got a little example. Where is it? Here. Here's a difference between two types of DNA. One's the RNA, the other one's the DNA. Okay, and they both use CHON, C-H-O-N. In other words, they use carbon, hydrogen, oxygen, and nitrogen. But the backbone of these guys is made of phosphates, and what they are, is phosphorus-based chemicals or compounds. So even though we identify life with CHON, there's always some other elements going on, just like with air. Okay, so air has other trace elements, but we always refer to anything living as being made of CHON. That's it. It's like we don't mention any of the other chemicals, but in your body you got other chemicals, among them iron. Here's an article. Okay, let me put it over here. And just one pulled out at random. Okay, crucial cellular processes such as DNA synthesis and the generation of ATP require iron. Okay, viruses depend on iron in order to efficiently replicate within living host cells. In other words, this virus that's going around, hey, we could kill it if we could remove all the iron, because it needs iron. You say, well, the virus is CHON, right? Well, it needs iron as well, and maybe phosphates, and who knows what. So, when I say air, I'm referring to O2, okay? And just like when you say something living, you primarily refer to CHON compounds, but there's always some other trace elements in your body for sure. Okay, another comment. Person says, my argument against inbreeding and DNA genetics is that the only thing we know about inbreeding is to not do it. Okay. How you stop inbreeding is by not having sex. Correct. That's true. That's the only way you can stop inbreeding. Well, that's one way. The other one is to breed with some other animal, some other species. Hopefully an animal species, not a plant one, okay? And you have sex with this other species, and somehow you produce some kind of offspring out of that, and if you do, well, then you're going to have genetic diversity. No ifs, ands, or buts about that, okay? Inbreeding, can't say when it started, irrelevant. So it doesn't matter when it started. Whenever it did start, it means from that point on, we never bred with another species. That's all it means. We bred within the species as it evolved, okay? So that's inbreeding. Inbreeding means you don't have sex with a cow or with an elephant or with a shark. Okay, what you have sex is with another human, and they have to be very closely related in order to have viable offspring. What does inbreeding have to do with a damn trade and economy? Absolutely nothing. I don't know where you got that. Fellow doesn't speak good English. Apparently, I guess he's foreigner or whatever. I don't know. But yeah, it has nothing to do with economy. The issue there was the context there was that inbreeding leads to some of the problems that we have today: homosexuality and autism and all kinds of mental and physical genetic disorders. Nothing to do with the extinction of man. The extinction of man has to do with one thing and one thing only. That's my theory here. With the extinction of money. Okay, the extinction of trade. When trade disappears, not if, but when it disappears, we disappear shortly thereafter. Okay, so the theory is that the economy will collapse. It has nothing to do with genetic diversity. Genetic diversity, all I'm saying there is that it leads to some of the genetic problems we're seeing today, which is towards the end of a species' life. Okay, and I mentioned a couple cases the other day, and that one was a passenger pigeon, another one's the Tasmanian tiger. They had low genetic diversity. They must have had also some problems within their species towards the end. Okay. Along the same lines, a fellow asks, you seem to underestimate the impact of epigenetics on overall disease. Okay, what is this gentleman talking about? Well, he's talking about this thingy here. Let me correct here. Talking about this definition of epigenetics: heritable changes in gene expression that do not involve changes to the underlying DNA sequence. Okay, so the issue here is that, the context. The context that I'm bringing up here is specifically that inbreeding leads to a loss of genetic diversity. I mentioned a couple articles last time. You can look at last week's video and you'll see the articles there. What I want to mention now is that one of the guys who analyzed family structures was Engels, and he said that at some point in time in the history of man, take it 200,000 years ago, 300,000 years ago, whenever you consider that humans began, where our species began, when we started inbreeding and never let go. At some point, we were during a long period of time, we were having group sex. In other words, fathers slept with daughters, sons with mothers, sister with brothers, cousins. It was a big mess, and nobody cared because we were quite out there in the wild. It's like any other animal. A lot of them inbreed as well within the family group. Okay, but what happened? According to Frederick Engels, who took material from Lewis Morgan, here I put him up here, he did a little study in the 19th century, and I think it's a good book to get started on the subject, okay? And this is what Engels does. He bases it on a book by Lewis Morgan, who was part of the a tribe known as he befriended a tribe called the Iroquois in New York State, and he wrote a book, Ancient Society, and based on that book, on the relations that he described there, then Frederick Engels wrote his book a few years later, The Origin of the Family, Private Property, and the State. And in the family part, he explains, he says, here the marriage groups are separated according to generations. All the grandfathers and grandmothers within the limits of the family are all husbands and wives of one another. So are also their children, the fathers and mothers. The latter's children will form a third circle of common husbands and wives, and their children, the great-grandchildren of the first group, will form a fourth. In this form of marriage, therefore, only ancestors and progeny and parents and children are excluded from the rights and duties of marriage with one another. Brothers and sisters, male and female cousins of the first, second, and more remote degrees are all brothers and sisters of one another. Precisely for that reason, they are all husbands and wives of one another. Okay, so this was a group marriage that existed during most of human history. Okay, we forget about all this stuff, and again, it's a theory, and you can come up with your own ideas, but you got to explain stuff. And what Lewis Morgan explained was why the Iroquois had certain names within their tribes, and why the kids belonged to this clan or to the other clan. So he was able to explain all that based on these relations. And he said that they must have existed, some of these relations, in the past, because otherwise he wouldn't be able to explain, the relations that he observed by living with these people, with this tribe. Okay, here's another comment from that book, and it's on the web, so you can at any point in time, just read it because it's there for free. Okay, you can look it up. The consanguine family is extinct. He's saying this in 1884, okay, 19th century. Even the most primitive couples known to history provide no demonstrable instance of it. But that it must have existed, we are compelled to admit, for the Hawaiian system of consanguinity, still prevalent today throughout the whole of Polynesia, expresses degrees of consanguinity, which could only arise in this form of family, and the whole subsequent development of the family presupposes existence of the consanguine family as a necessary preparatory stage. Okay, so he goes on saying that at some point in time we stop having these internal relations within the clan. Okay, and just a final one here so that you see what the context is. If the first advance in organization consisted in the exclusion of parents and children from the sexual intercourse with one another, the second was the exclusion of sister and brother. On account of the greater nearness in age, this second advance was infinitely more important, but also more difficult than the first. It was effected gradually, beginning probably with the exclusion from sexual intercourse of own brothers and sisters, first in isolated cases and then by degrees as a general rule. And he's saying that even in this century, exceptions were found in Hawaii, and ending with the prohibition of marriage even between collateral brothers and sisters, or as we should say, between first, second, and third cousins. It affords, says Morgan, right, a good illustration of the operation of the principle of natural selection. There can be no question that the tribes among whom inbreeding was restricted by this advance were bound to develop more quickly and more fully than those among whom marriage between brothers and sisters remained a rule of law. Okay, so all I'm saying is that we stopped inbreeding within the family, but that didn't stop inbreeding within the species. We continued to inbreed within the species. That means we had sex with another human. We didn't have sex with elephants or with monkeys or any other type of animal out there. That's called inbreeding. And when you take that inbreeding a long time, thousands of years, at some point you're going to encounter some serious problems, okay? Genetic problems. And that's where we are today. We're seeing the effects of long-term inbreeding, thousands of years of it, okay? And this is from my book where I say, how do you increase genetic diversity? Well, you can only increase genetic diversity at the beginning of a species lifetime. And a species is when it branches off from the main trunk. And here I give an example. And again, don't take these things by the letter because we have relatively little information. We make the assumption here that Neanderthal descended from Heidelbergensis and Heidelberg descended from Erectus. Okay, in between you could have antecessor, you could have other hominids in between, okay? But that's not important. What's important here is the graph. The graph says that genetic diversity increases at the beginning of a species' lifetime. Why? Because this species encounters new environments, new diseases, new ambience, and he's got to get used to this over thousands and thousands of years. That means that during this whole time, the genes that act to counteract or get accustomed to what's out there are not the same from the mother trunk where this species came from. Okay, so it needs to adjust. But once it begins inbreeding, once it becomes sedentary, then the curve can only go down. It can no longer increase because right now this species has become accustomed to endemic diseases, to the environment, the whatever, cold, hot, or wherever you are at. And so it has no need to change its genetic structure. Meanwhile, it's inbreeding. It's having sex and offspring with those that are very close, around them. And so, yes, this is what happens over a long period of time. And my argument is that if you do this for many thousands of years, what you're going to do is eventually lose your genetic diversity. Okay, here's an example of that. We have this map, and you see Africa there. You have zebras and lions, and then you see the Arctic. You have maybe elk and polar bear. Okay. Now, what would happen if you take a gorilla? Okay, a gorilla decides to migrate, from Africa all the way to the Arctic. Okay, and wants to live there. Well, let's assume this takes thousands and thousands of years. That trek. Okay, so this gorilla or this group of gorillas or bunch of gorillas, they eventually migrate northwards. Well, they left a very warm region, in this case the equator, to go into a very cold region. Well, some of the defenses that they had are no longer useful to this gorilla. Now encounters new environment, new diseases. So different parts of his DNA and his genes work to offset the bad things and make the most of or expand the good things within his body. So he's going to change genetically simply because of his adaptation to the new environment, to the new diseases, to everything that's new, maybe predators, okay? So that gorilla, if you find him thousands of years later, he will not have the same genes that he had when he started. And so that means that during this time, he could conceivably, the way I look at it, increase his genetic diversity. It's only when he settles down, becomes sedentary, that he's now at home. He's no longer migrating. And now he gets used to whatever he's got, okay? And that includes diseases. Over time, he conquers them. A lot of people die, or a lot of members of that species die over time, but eventually they become accustomed. Those who survive, they become accustomed to those diseases, and now those diseases don't kill them anymore. If anything, it makes them sick. That means that those outliers that you had in the genetic pool, those are gone because they couldn't stand the new conditions. And what you're doing is limiting or streamlining your genetic diversity. That's, I think, what the process is. Okay, that's the way I look at that. Okay, another comment here. Someone thinking is irrational since none has ever saw DNA. Yeah, I think seems like your thinking is irrational because first of all, let's make sure we understand the language, okay? He says your definitions aren't rigorous. It looks like the other way around. You can't say you see DNA, okay? DNA you watch because it moves and so on. But we don't need to see DNA, okay? We don't need to see DNA. In science, we do not use our eyes and we do not use our hands, okay? And it takes a long time for people to understand that. They have this notion of science from when they went to school or college or whatever, and they have this idea you got to prove things, that you got to demonstrate things, that you go in there and you do an experiment in the lab, you observe, you know, you run a test, maybe you measure. None of that has anything to do with science. Okay, let's get that straight up front. Science, explanations. That's it. You got to explain something. We don't care what you did in the lab. We don't care if you did an experiment. We don't care if you used your hands, your eyes, if you saw, you didn't. We don't care any about that. When you come to the conference, we want you to explain a mechanism. That's what science is about. So whether you see DNA or not is irrelevant. You can make an assumption, say, let us assume that DNA exists and it looks like this. We're done. That's it. You make an assumption. Now what are you going to explain with that? That's what we're interested in. Okay, so whether you saw or not, whether you use your eyes, your hands, whether you did an experiment, we don't care. None of that is relevant to science. Okay, DNA, what's that? Well, here, let me show you what's that. DNA looks like this. Something like this. Let's see if I can get it up here. Got so many of these. Takes a while to get up, just to get them up. There you go. That's what it looks like. Okay, a bunch of dumbbells in a row. DNA is simply a is a big molecule. That's all it is. Okay, and you don't have to believe in DNA. You don't have to accept it. That's not important. What's important is that the person who comes into the conference says, look, this is DNA. With this thingy here, I'm going to explain this other thing. It's the explanation we're interested in. Okay, that's the way it works in science. So you can point to whatever you want to point to. It doesn't matter. Okay, your theory, your explanation should follow from whatever you pointed to. Okay, so yeah, whether you saw or not, whether you believe in DNA or not, irrelevant. Totally irrelevant in science. In science, we do not believe in God. We do not prove God. Science, we make an assumption, say, let us assume that God exists. Okay, now what's your theory? Well, I theorize that God created the universe, and this is how he did it. That's what we want to hear. Okay, we don't want you saying, oh, I believe in God. Oh, I know God exists. That's irrelevant to science. DNA, what's that? None can see that. If you can show me DNA, I just showed you DNA, need a rational explanation we can see. No, we don't see rational explanations, for sure. And we do not use our eyes. What we see is what the person pointed to on the board or in his presentation on the screen or whatever. And that's this here. There it is. That's what DNA. Now you saw it. For the first time in your life, you saw DNA. Okay? That's what DNA looks like. Whether you believe or not, irrelevant. Okay? The only way to see trade is to have trade. You don't see trade, and again, this fellow has his world upside down. He sees trade. Trade is a verb, and in science, okay, and so you don't see verbs. What you do is watch verbs. So let's get it right. Let's get the language right first. Okay, the language is here. You got the all-seeing eye. Okay, and what you see is pictures, images, still images. What you watch is movies. Okay, so you need to use the language correctly. You don't see trade because trade is a movie. You can watch trade happen and you can see the Mona Lisa, but you can't see a movie. Okay, you watch it. Okay, so let's get the language straight. And so yeah, the DNA, it's just an assumption. You can take it as an assumption. Now, there's a theory also out there that you can, which concludes on DNA. You can say, look, I think what's causing all this stuff in your body is DNA, and this is why I think that's the case. And now you work your way all the way to DNA because you have a theory of why that's the case, of what's causing something to happen. Okay, you're explaining a phenomenon, and you end up with DNA and say, look, this is what I think it should look like. Okay, now whether you believe that or not, that's your personal problem. We don't care. The guy's explaining how he ended up with DNA. Then another guy picks up DNA and uses it as a foundation for his theory. He says, essentially, he's saying, let us assume that DNA exists and look like this, what I just showed you, okay? And from this, I can explain this other thing. So again, these are assumptions that you make in order to explain a theory. You should go to scientific conferences more often, and you'll find that it's about explanations, except in mathematical physics. Okay, they don't do explanations, but that's what science is. Science is explanations. And yeah, we begin with assumptions. You have to make an assumption, especially about invisible entities such as light, gravity, and so on, possibly even DNA, atoms, you know. Okay, along the same line, Fowler says entropy varies directly with any reversible change in heat in the system. What what is heat? Okay, he's asking. Um, well, heat under I can only tell you what heat is under the rope model, and here it is. This is what heat is under the rope model. Okay, okay. If you look at the top one, you have two atoms quantum jumping, and they're jumping a little faster than the ones in the middle, and which are pumping faster than the ones at the bottom. Okay, and you can see that what changes also the length of the links, and the frequency obviously changes. Okay, so you have the velocity of light there synthesized in those three sets of atoms. So what is heat? Well, as you go up, you get higher heat. Why? Because you have higher energy. Remember the word energy? No definition? Well, now you do have a definition. Definition is that higher frequency, shorter wavelength, in other words, the link length, is what gives you heat. And the slower it goes, the closer you approach coldness. Okay, so that's the model under the rope model. Okay, the model for heat, you can say. Okay, and he had another question here. Let me get that back in here. And that is that what is a closed system and can that exist? The universe need definition can be considered a closed system. Yeah, in fact, I have said argued that the universe is the only closed system. Okay, and here let's go through that real quick here. Okay, universe, matter, and space. That's the definition of universe. Space, that which doesn't have shape. Okay, now we know what it is. In other words, space is not a what. Okay, we define space, and it's a synonym of vacuum, and it's a synonym of nothing or nothingness. Universe and space are not objects. Universe and space are concepts. Objects we point to. We can't point to a concept. Okay, so what we do is define it. Okay, that's where we start. Now, in my book, Why God Doesn't Exist, here's the what I said about closed system. That which is entirely isolated from external inputs of temperature, gravity, or other electromagnetic activity. Closed system is an environment or a medium that is infinite, quotations there, okay? A place. Place obviously is infinite in the sense that it has no borders, it has no limits, no boundaries. Only that which has no boundaries can be a closed system, right? Because nothing can get in, nothing can get out, because there's no boundary to cross. We now have the necessary ingredients to postulate that our universe is a perpetual machine, the only one conceivable. The universe was not created, never had inputs, had no kickoff, and will have no end. If matter cannot convert into space or space into matter, and space has no boundaries, the universe as a whole is a closed system. Matter exists in present mode and not in future or past modes. In this sense, the universe is definitely perpetual. Space is a place. This makes our universe the only conceivable closed system. Cause and effect implies that there is no first cause or last effect. We live in what we could call a perpetual machine. That's essentially what a closed system is, okay? A perpetual machine, because it cannot receive energy and it cannot lose energy, because there's no boundary for the so-called energy to cross in either direction. Okay, and here I try to illustrate this for you a little bit. Okay, let's see if you can visualize this. Okay, here's our universe. Oh no, wrong one. Sorry. Let me get this one here. Here it is. Okay, here it is. Here's our universe. Okay, all the matter in the universe. And the black stuff is space. Nothing. Vacuum. Okay. Now you can see the particles or galaxies or stars, whatever, they're expanding. They're expanding. They can get away from each other maybe momentarily, then come back. They maybe oscillate back and forth, but no particle can leave the universe, the space, because space is not a thing. It has no shape. It has no boundary. So none of those particles has any possibility of getting out of the universe. Okay, that's why it's perpetual. Okay, it's also a closed system. Okay, and here the opposite of that. No particle, no entity can come into our universe. Okay, here's some particles trying to get into our universe. That can never happen. One of the two, either those particles are part of our universe, okay, or they can't come in. Because there is no other universe, because space has no boundary. So those particles had no boundary to cross in order for them to come into our universe. Okay, it's very difficult for you to understand that, but see that space there that ends at the four corners of that frame, it doesn't end there because space has no boundaries. So if it has no boundaries, where are those particles coming from? What boundary did they cross if space has no boundaries? And if those particles did come into our universe, it's because they were part of our universe to begin with, because space has no boundaries. Okay, and so I'll let you stew on that one for a while, because it takes a while to understand that. Okay, now let's give you another image of this. Okay, here we have three universes. Okay, let's assume there are three universes. We have three blocks of matter, and ours is one of them. Okay, so we have one of those is our universe. Okay, now what happens if space is not a thing? Okay, space has no boundaries. Then those three universes are really one. Okay, we're not isolated from them, because in the sense that even if we have a block of matter over here, it doesn't preclude that that other matter over there, which is just far away, is part of our universe. Okay, so if space has no boundaries, all those three universes are a single universe. Okay, and so we can't say that there are three universes. It's a single universe. Okay, all we have is just different distances between blocks of matter or bunches of matter. And this is more or less what galaxies are. Okay, galaxies are simply clumps of matter, stars primarily, right? Gases that are isolated by distance from other galaxies. Are those galaxies different universes? Well, no, they're all part of the same universe, because space is not a physical entity. Okay. Now, let me give you another scenario here, just for food for thought for you. Let's assume that all the matter in one of those universes is isolated physically for some reason from matter of that other universe there, of one of the, or both of those other universes. Okay. Now, it could be that within our universe, the speed of light is 300,000 kilometers per second, but it could be that in one of those other universes, or both of them, they have different speeds of light, and other constants are different. Maybe the what is it? The mass of the electron is different, etc. Okay, why? Because they may have different. Because they could be isolated by what I'm going to show you next. They could be isolated in a sense that even though they are part of our universe, they have different sets of laws, because none of them are connected in any way to our universe. What am I talking about? Well, I'm talking about what happens under the rope model. See, under the rope model, you have this situation. Okay, let's assume two of those universes are connected or interconnected by electromagnetic ropes. Okay, then they are part of our universe, and the speed of light is the same in both universes, because there is no difference between them. But let's assume that those ropes, like in the first case that I showed here, are only within each one of these universes. In other words, they don't have the same ropes connecting them, interconnecting them. Then yes, they could have different speeds of light, because the speed of light is determined by the amount of matter in the universe. But in each of those universes, if those universes for some reason are not connected to each other. Okay? So that's your food for thought. I hope you understood the thinking. So you don't have that situation under quantum and mathematical physics because all they talk about is particles and all the particles are not connected to each other. So they can talk about universes without knowing what they're talking about because they never define the word universe. If it's matter in space, there is no other thing except one universe. Under the rope model, if our universe, if our ropes from every atom in our universe is not connected to that clump of matter that forms a different universe, they could have another clump of matter. They could have ropes interconnecting their atoms. None of those atoms are connected to the ones in our universe. In that case, they could have a different speed of light and different set of rules over there. Okay? And what's interesting about that is that these two universes, imagine them crossing each other. Okay? We wouldn't be able to see any other matter in that universe. Why? Because the only way we see light is because a rope is connected to our eye from the atom across the street. And what happens is none of those atoms are connected to our eyes. You understand the problem? So the rope presents some very interesting philosophical things. I mean, this is just food for thought. But the rope model presents you with the possibility that there are different universes within our universe. And what do I mean by that? I mean that the ropes from one clump of matter are not connected to the ropes of another clump of matter. That's the issue. Food for thought, just speculating. Okay, that's all it is. Okay. Okay, moving on here. Otherwise, I'll spend all day here. And again, I'm going to be putting the timestamps later on so you can jump across the stuff that you don't want to read about. Seems like all objects would have to be 3D. And no, again, an object is that which has shape. I'm going to show you a shape that is not 3D. And here it is. There it is. It's known as a triangle. Okay? Triangle is not 3D. A triangle is an object. For the purposes of physics, not ordinary speech. In ordinary speech, we think of objects as that which can be touched or seen. We think of objects as that which is 3D. And they never clarified that either because the table I'm thinking about, that's 3D, but it's in my head. It's not out here. So it's 3D, but you can't see or touch it. And nevertheless, we have there a triangle. It's got shape, but it's not 3D. So it meets the definition of object. It does not meet the definition of 3D. Okay, so hope that I clarify that one. Here's another issue. Okay, along the same lines, completely empty hole in the thread have shape, but it's not an object. My point is the object is that which has surface because sometimes shape is not perfect to define. Yeah, we don't have to define the word shape, not in science. Shape, you want to know what shape is, go to kindergarten, ask the children what's the difference between, a ball and a cube. Just show them this and say, what's the difference? Assuming they're all the same color, same material, same everything, same volume, same mass, whatever. Just show them two things like this and say, what's the difference? They'll tell you the shape. And they'll teach you what shape is. We don't need a definition of shape. We need a definition of object. And the definition of object is that which has shape. So there we go. And shape is what you learn out there every day, okay? We know what shape is, so we do not need to define that term at all. We don't define every word in the dictionary, okay? Not in science. We don't need to. Only those that make or break our theory. And right now what we do with, in the case of the word object, we have to compare it against other possibilities. We have to compare it against those who define it as motion, as volume, as mass, as see, as touch. That's what we're comparing against. So you don't have to ask what shape is. A shape is understood as much as motion, pretty much is understood, mass, touch, see. We don't need perfect definitions of those words. All we need to know is the difference between shape and touch, or shape and motion, or shape and volume. If you can tell the difference between those words, you don't need to define the word shape. That's the issue. When you ask for the definition of shape, you're trying to get run on a tangent. You're trying to get away from the discussion, usually trying to avoid punishment. And usually it's devil's advocates who do that. Okay, object, and also we can create shape to emptiness, but we not create surface to it. So according to me, surface is not is best criteria to define object. Okay, pigeon English, very hard to understand this guy. My definition of object, that which has surface is object. If any problems with it, my definition is please explain it. Please explain it. Yeah, okay, I'll explain what the problems are with your definition. Your definition is clearly has many flaws, okay, and here it is, a rundown. First is that surface is a 3D concept, okay? Not all objects are 3D, again, and so surface only belongs to 3D. Circle is 2D, for example, or I just describe, what is it, a triangle. Plane is 2D, a surface is 3D. An object, 3D, is ordinary speech. So anytime you use the word surface, you're talking about 3D and you're talking about ordinary speech. Okay, you're not using a scientific definition. Very easy to destroy the word surface, okay? And here, again, I want to show, give me a second here. I want to show some of the problems. First, you can't and don't need to define three components to make shape. See, right there, you got three components. What this fellow is saying is that if you enclose space within some kind of boundary, in this case, a circle, okay, what you end up with a sandwich. You end up with space, ring, and space. That's what you end up with, okay? And so, people try to enclose space and say, space does have has shape as well. No, space does not have shape, because the only thing we have that has shape there is the ring, okay? And the way we're supposed to look at this as a continuous body, you have to look at it like that. There's only two things, or two entities, or words treated as entities that make up an object. One is space, which serves as the backdrop, and the other one is whatever's enclosed or contained within the boundary, okay? So what's inside the boundary perimeter is not the shape. Shape is what is enclosed, encapsulated by space, the region within the boundary, okay? You must treat the what's inside the boundary as if it's made of a single piece, okay? Again, we don't accept mereology, which is what an object is made of. And you can't contain, encapsulate that which doesn't have shape. So you haven't contained the space within a ring. Okay, space just went right through you because space has no shape. So you have nothing to contain. Okay, and just to rub it in, because people also bring up the issue of what is flatness. Okay, and here I try to clarify that as well, because it relates to this issue. Whether a boundary, a ring, whether you should consider the ring or the disc, okay? And a disc is flat, unless you turn it sideways. You might see some thickness, in which case it's 3D. Otherwise, a ring seen head on is 2D. Okay, that's because it's on a 2D platform. You have to make no assumptions about that having any width or thickness. Okay, but here you have the flatlanders, and we have them in relativity, and we have the Flat Earth Society. Okay, and what do you see there? What you see is what they define as flat, and flat earthers, they never define flat, because flat means zero thickness, and they want you to think that flatness is a surface that is smooth, okay? But see, for a surface to be smooth, you got to pass your finger around. You got to do a test. And again, even in that case, the flat earthers lose, because you got Mount Everest, and it kind of is not flat like at sea level, and so the earth is not flat. And so when you ask them, how flat is flat? I mean, what do you mean by flat? So we have to define this term, especially we're going to talk about, flat earth and flatlanders and relativists who say the universe is flat, okay? And so the way we do it, we say, yeah, zero thickness, okay? That's flat, okay? So you can see even in Einstein's flat universe, they put a little bit of thickness there. That's not flat. but they give you the impression they know what they're talking about because they don't define these crucial terms when they just say, oh, what is flatness? Okay, pancake is not flat, not in science. Okay, in ordinary speech, a pancake can be flat. You say a flat is a pancake, not in science. Science, it's got to have zero thickness. And zero thickness, you can say, is a triangle because it's 2D only. So by definition, has no depth or width or thickness or whatever you want to call it. Okay, and so yeah, that's the definition of flat. Once you define that word flat, now it becomes difficult for them to make their case, and the only option they have is to define flatness in the alternative. That's all they have to do. Okay. Here's NASA's flatlanders. Okay. Okay. They believe the Earth is flat. The universe is flat. Okay. And they say they proved it. And how do they prove it? Well, first of all, the problem is that they define flatness by measuring. And then they treat universe as a physical object. So they say the universe, like if it's a physical object, is flat. They illustrate it as flat. So they're talking about a board. They're saying the universe is some kind of finite board that I guess has zero thickness, because if it is completely flat, I mean, what else can they refer to? Well, what they say is they're going to measure. They're going to measure flatness. That's how they determine flatness. And you can see all the verbs they've got. They're talking about collapsing, expanding, okay, accelerating. So the words that they're going to use are all dynamic. That's how they determine flatness. And yeah, this is the problem of why, you know, no one in mathematical physics defines words, and that's a serious problem because we don't know eventually what they're talking about when they say flat universe. And again, they want to do it with motion. They say they're going to measure flatness. And no, first you got to define flatness before you do anything like measuring. That's one issue. The other issue is that flat is a static concept. You do not determine flatness by measuring, by running the, I don't know, your measuring tape or whatever you're going to use. We don't determine flatness. We define flatness so we know what we're going to determine before we go to the lab. Okay? So you got to define flatness. And if you're going to use dynamic concepts to say, well, this is how I'm going to measure flatness, well, then you haven't defined flatness. Flat belongs to geometry, and flat means 2D, essentially. That's what it means. So there's in a plane meaning plane geometry, right? Plane is flat. That's flat. Okay. Anything, any use other than that is mere opinion. Okay, and one last comment here before we get on to the subject today. Jesus. Okay, and here is a shape. Okay, and you might say, well, hold it, that shape, it's got a backdrop. It's a black backdrop. And people focus on the flat backdrop, on the black backdrop, and they say, well, what is that? And does it have limits right there? Is it limited by the frame? And you know, they have 1,000 questions. No, you got to focus on the object, on the shape that the center of attention is what's in the center. That's what we're referring to. Don't look at the black stuff at all. Don't ask about it. That black stuff is known as space, nothing. And here, let me change the backdrop so that I confuse you completely. Okay, you want to put a watery, oceany type of backdrop? Go ahead, no problem. You want to use a curtain? How's that for a backdrop? Okay. Don't ask about the backdrop. The backdrop is not important. And here's the blue sky backdrop. How's that? You can use any backdrop you want. We call it space. And it's not infinite. It simply has no shape. The only reason we give it shape is because we have to put some frame around it. Okay, but the issue is it's the object in the center that we're concerned about. That's an object for the purposes of physics. Okay, so this notion about criticizing the space and what it's made out of, etc. Very simple. Space is nothing. It's just a backdrop. That's all it is. There is no such thing as space. Okay. Okay, I hope I answered some questions regarding objects and shape. Okay, there. Okay, let's get on with Mr. Al-Khalili. A little late, but again, you know, you can skip over the stuff you don't want to read about. And here's my summary of what I'm going to talk about, or my criticisms of Adam Man Jimmy there. These are his fatal flaws in his arguments, okay? He argues that he learned physics by rote while standing on the shoulders of giants such as Rutherford, Bohr, Heisenberg, Born, and Chadwick. It turns out that these fellows, you know, they were not giants. You know, I think they were mental midgets, pygmies, dwarves. The conclusion of these mental midgets is the Copenhagen interpretation of QM. That's the one he concludes with. He says that's the one that's active today. That's the one people believe in the mathematical world. So that's the one you got to respect, okay, supposedly, or take on the basis of authority. The Copenhagen interpretation essentially states that you cannot even visualize the atom. So don't even try. See, people talk about the atom and what it looks like, and they draw a little ball going around the, you know, the planetary model, the little ball going around the nucleus. No, don't even try to look at or to visualize it, because the Copenhagen interpretation says you cannot. You're an irrational individual if you try to visualize the atom. Okay, so please get that straight up front. If you thought otherwise, well, you got a problem, okay? The only way to approach the atom is through mathematical description. That's the Copenhagen interpretation. That's what Jimmy's going to talk about. The mathematicians refer to this description as a theory. A description is not a theory because a theory is an explanation. So there is no such theory as quantum mechanics, primarily because they don't have objects. Okay, they don't use objects, so whatever explanation they give you is irrational, and so I'm not sure it qualifies even as an explanation. I mean, if someone uses magic to explain something, has he really explained it? So there is no such thing as quantum theory. All there is quantum description. Description is not theory. Okay, quantum only describes. And the result, everyone simulates quantum mechanics with a planetary model, you know, the atom, okay, and treats the atom as a solar system. Like with gravity, no one can justify why the electron or the Earth doesn't spontaneously fly away. That's the key issue in quantum mechanics and also in relativity. They cannot explain the force of pull. They cannot explain why the electron spontaneously doesn't fly away. That's the only question you got to ask any quantum guy, any. Soon as he says, oh, quantum, and I study all these years and I'm an expert, okay, say, tell me why the electron doesn't spontaneously fly away. What keeps it bound to the nucleus, to the proton? Same with the Earth in the case of relativity. Yeah, they tell you that the Earth goes around the sun, fine. Now you ask them, why doesn't the Earth fly out of the solar system spontaneously? And what are they going to say? That time is warped and that's what prevents the Earth from flying out? You're going to say, well, time is a concept. How does time come in contact with the skin of the Earth? And a guy might tell you, it's just an analogy. You're not supposed to take it seriously. That's the answer they'll give you. You know, they have no answer. So they don't have an explanation for why the Earth doesn't leave the solar system. They don't have an explanation, a mechanism for why the electron doesn't spontaneously leave the atom and fly out. Why do you have to spur it or stimulate it into leaving the atom and turn it into an ion or maybe to conduct electricity? Why do you have to do something to it? Why doesn't it automatically, spontaneously, the electron, why doesn't it spontaneously leave the atom? That's the only question that quantum has to answer. And of course, they'll never answer that because you can't do it with particles. It's the particle hypothesis, which is nonsense, which has to be debunked or thrown away, thrown in the garbage can once and for all. It's the particle hypothesis which we've been using for the last 10,000 years. Okay, here's Adam Man Jim Al-Khalili. He starts out more or less, you know, saying that everything's made of atoms. He said, we asked where we had come from, how were the stars created, how all the elements were made, even how the universe itself had begun. And here he just tells the biggest fib that ever told. He says, One of mankind's greatest achievements is that we've answered these questions. Oh, you have? Please answer why the electron doesn't spontaneously leave the atom. That's all you got to answer. And he can't answer that. So no, he hasn't answered all these questions. He's giving lip service. He's giving you a sales job here, okay? He's selling you something. He's giving you a false advertisement. The atom has helped us solve the greatest mysteries of existence. Has it? Okay, that's great. We don't know what an atom looks like, but he says it solves all of our problems. This is the story of the greatest scientific discovery ever. The discovery that everything is made of atoms. That's so strange that he would start his talk like that, because here you have a fellow which he mentions, and that's Mr. Ludwig Boltzmann. And Ludwig, good old Ludwig, he came up with the idea that the atom is real. Okay, he in the 19th century, towards the end of the 19th century, he was arguing that there are for sure real atoms. No one in those days seemed to believe that the atoms were for real, because no one could see them or touch them. So they say, no, it's just a hypothesis. It's just something that we invoke. We say, oh, the atom, but there's no real thing called the atom. And it turns out that Boltzmann, I don't know, he's given credit for this by Jim Al-Khalili, but Democritus already said that 2,000 years ago. He said, all that exists is atoms and empty space. I mean, how much more clear do you need it than that? So no, Boltzmann was not the first to mention that for sure. He says that Boltzmann committed suicide. He hung himself in 1906 because no one would believe him. No one accepted his version that atoms were real. Okay, but here, good old Einstein, he came up in 1905, a year before Boltzmann's death. And he wrote 4 papers in 1905, annus mirabilis, so-called. And in one of them, he explains Brownian motion. Guy in 1827, Mr. Brown, and he discovered that all these pollen were moving inside the water, and he said, why are they moving? They called it Brownian motion. And Einstein explained that in 1905, one of his 4 papers that he published that year. And he explained that, and he says, Al-Khalili speaks for Einstein. He says, the pollen will only jiggle if they were being jostled by something else. Correct. I totally agree. We don't need Einstein for that. We don't need Boltzmann. We don't need Democritus for that. All we need is common sense. If something is moving, and physics is done with objects, first rule of physics, right? Then there had better be that something invisible, intangible, that is moving that pollen. They're bombarding it. And I talked about that in my last lecture. Okay, so you can see the movie that someone showed there. I essentially put it up, as an MP4. And you can see these particles. You don't see these particles, but you see that something's bombarding whatever's moving there. And those invisible, intangible thingies are thingies. They're particles of some kind. You can speculate whether they're round or cubic or whatever, but there's something there. You can't say there's nothing there simply because you can't see or touch it. And that's why we don't need Einstein to tell us, that pollen was being moved by particles called atoms or molecules. So Einstein said that water must be made of tiny atom-like particles which themselves are jiggling. Correct. And again, it just follows from the first law of physics, which is physics is done with objects. You can't do it with concepts. You can't do it with magic. Okay. Einstein proved that for Brownian motion to happen, atoms must exist. Now, he didn't prove it. There's no such thing as proof in science. All you do is you make an assumption. You say, you can say that there's something elongated, or there's a battering ram, or there are little particles. You can speculate on a lot of this stuff, but there better be something there. There better be something that's causing that. You can't say it's done with concepts, okay? The atom had to be real. Of course it had to be real. Now, if you want to call it an atom, which is what I call it, because this is what the word out there that's used, no problem. You want to call it X, but X had better be a physical object. That's the point, okay? And you can put it as the devil if you want, or God, or whatever, but it better be something. It better have shape, okay? Okay, so from there, what happened was they started looking at the atom, and here we have Rutherford. He tried to peer inside the atom. He ran his gold foil backscattering experiment, which is there more or less illustrated. It says Rutherford pictured the atom as a tiny solar system. Electrons, tiny particles of negative electricity, orbit around minute, positively charged objects called the nucleus. That's why um, 1 in 8,000 alpha particles bounce back. They're the ones that hit the tiny nucleus by chance. The rest went by without hitting anything. Rutherford's atom is almost entirely empty space. That's why nearly all the alpha particles raced through the gold atoms as if there's nothing there. There really is nothing there. Well, it's interesting that Al-Khalili would say all this after he says that nothing doesn't exist in quantum mechanics, that nothing is made of particles, which is what I talked about in my last lecture. I mean, he spent a whole hour telling you that nothing is made of something, and now here he says that atom is mostly nothing, which means an atom is mostly something, a bunch of particles. And what are those particles? Well, they're these particles that negative and positive, matter, antimatter, electrons and positrons, that they, and I like to explain it this is the way I like to describe this. I'm saying that you take a black ball and a white ball, you put them together and you create a no ball. And likewise, the no ball can reverse the process and turn it into a black ball and a white ball. That's essentially what these people are saying. They call it positive, negative, antimatter, matter, etc. Okay, what's the problem with that? In fact, Al-Khalili says if two particles, one antimatter, the other one matter, collide or meet, right? Oh man, it's the end of the universe because all that energy is released. And then this dummy, because there's no other word to describe him, he says that our space is constantly having all these particles, no particles, convert into white and black particles, which immediately recombine, right? What happens when you recombine matter and antimatter? Well, you have all this energy, all this big explosion. And here he's saying this is happening constantly in this nothingness that we call empty space. So all this jiggling that's going on there between matter and antimatter is supposedly every time two particles collide of matter and antimatter should release gazillions of energy, whatever that is. And it's happening in every little bit of space. It's constantly coming out and coming in, coming out and coming in. So we have all these explosions that should be destroying the entire universe. And they say these things, they don't even know what they're saying anymore. They just say whatever comes into their mind. And now they're saying that Rutherford says an atom is mostly empty space, which is what? A bunch of particles. So an atom is mostly a bunch of particles. Okay, now we got it. We got it straight. Important to keep it straight, right? Okay, but Ruthy had a little bit of problem, okay, because here he ran into this problem where it says almost immediately a problem surfaced. The electron should lose their energy, run out of steam, and spiral into the nucleus in less than a blink of an eye. Rutherford atom contradicted the known laws of science. Not surprisingly, all the established scientists of the day, including Einstein, were baffled. Scientific ideas they put their faith in all their lives had failed completely to explain the atom. The atom now required a new generation of scientists. Listen to this. It was crucial they had no loyalty or attachment to ideas held by the previous generations. Okay? So first, if you want to make progress, you got to stop listening to your teachers. That's essentially what these guys were saying. New generation came in, overthrew the old generation, and said, you guys are classical mechanics, we're doing quantum mechanics. And so he had to explain why the electron doesn't spiral into the nucleus. And that's when Niels Bohr comes around, okay, according to Al-Khalili, which is right. He's just reading history here, essentially, okay. And here's Niels Bohr, and he says, look, I'll tell you why. Because, what the electron does is quantum jump. Just goes back and forth between so-called energy levels, whatever that was, and that would explain in the spectrum of light, Okay, and Bohr made it his mission to solve the problem of why the atom didn't collapse and why there was no such why there was so much empty space, which is what? A bunch of particles, right? As one of the new breed of theoretical physicists, he was prepared to abandon common sense and human intuition to find an explanation. Bohr's idea was to take Rutherford's solar system model of the atom and replace it with something that is impossible to imagine or visualize. Aha! So here we went into abstraction. We no longer had an atom. Now we had this abstraction, which was just an explanation. Says the little, not even an explanation. It's really a description, but he says it explained the behavior of light. Okay, that's essentially what he was trying to explain. So he explained that, but what he did, he gave an irrational description. The description was that this little bead just went back and forth between so-called energy levels for who knows what reason. So Bohr's idea was to take Rutherford's solar system, model the atom, and replace it with something that is impossible to imagine or visualize. Of course, sensible ideas like empty space and particles moving around in orbits fade away, and they're replaced with the nonsense called quantum jump. Why does that little bead go back and forth? That's what they got to explain, and of course they did not explain that. They just described and says it does, so that's it. In fact, Niels Bohr, there's one person who questioned, or at least one person, I don't know, questioned, and he said, yeah, maybe we don't understand it, but it happens. Okay, so what was Niels Bohr analogy for what was happening with the electron? He says he described the atom not as a solar system, but as a multi-story building. The ground floor is where the nucleus lives, with the electrons occupying the floors above. Mysterious laws, always mysterious, right, mean that the electrons can only live on the floors and never in between. And other mysterious laws mean that sometimes they can instantaneously jump from one floor to another. These are what we call quantum jumps. Okay, so what we have here is a notion of what quantum thinks is happening inside the atom. And again, it's all mysterious. Why? The reason it's mysterious is that they're trying to do it with particles. That's why it's mysterious. Once we abandon the particle, we've got it made. As long as you insist on the particle hypothesis, which is what quantum is all about, or waves, which is, again, particles, because what is waving? Particles. So you have two options. You can take the Newtonian version, which is, you know, these particles essentially ran straight, and they were not the vibration of the ether, or you can take the Robert Hooke and Huygens version, which is the vibration of the ether, the particles of ether. But it's always been particles or nothing. They have no other option. No other option has been put forth in the last 10,000 years until we now have the rope model. Pull. For the first time, we have all atoms are interconnected. That was never proposed, postulated by anyone. Okay, so that's new. That's what this site is about. Okay, so so we continue here. Bohr went in there and says, when one physicist claimed that the jumps were nonsense, Bohr replied, yes, you're completely right, but that doesn't prove the jumps don't happen. Only that you cannot visualize them. So if you cannot visualize it, what kind of science is that? What kind of physics is that? Hopefully, if you're going to explain a mechanism, we can all visualize it. If you can't visualize the mechanism, then what kind of mechanism are you proposing? And this is where you can see that quantum got farther and farther away from physics into complete abstractions, irrationality, surrealism. Okay, because now for the first time, they no longer talk about what you can visualize. Okay, now they talk about complete mathematical nonsense, abstractions, and that's why to this day they tell you, oh, if you want to understand how the what the atom looks like or what it's like or whatever, you got to take math. That's the answer. But not being able to visualize things seemed to go against the whole purpose of science. Correct. It does go against the purpose of science. Older scientists, in particular, felt that science was supposed to be about understanding the world. Correct. not about making arbitrary rules that seem to fit the data. Boy, he said it perfectly there. Yeah, that's what science is. Science is about explaining rationally a mechanism. And if you say, I cannot visualize it, but here's the theory, you don't have a theory. What you have is magic. That's the issue, and that's what Bohr and Heisenberg and some of these other guys finally ended up with. They ended up with abstractions saying that's the world, that's the way the universe works at the subatomic world. Okay. Okay, so we have this fellow, Mr. Schrodinger. He comes in there and he says, "Oh, I can tell you what the atom looks like." He tried to have a picture still of the atom. He based it a little bit on what de Broglie suggested, which is that you have integral waves. The electron has integral waves around the nucleus. And Schrodinger came up with a similar idea. He just came up with his equation. He said the electron, essentially this is his interpretation, the electron is in fact a wave of energy, whatever that is. There's no such thing as a wave. There's no such thing as energy. So we still have abstraction. What are we staring at? We don't know. Vibrating so fast it looks like a cloud. So all we have is a bunch of abstractions. Again, we have no real atom there. We have wave of what? Of energy. What is energy? Oh, we don't know. We're still trying to figure out. We're still trying to define it. A cloud-like wave of pure energy. So what have we learned? What is an atom? Just energy is a concept. Wave is a concept. So we have the waving of a concept. That's what an atom is. So he had a problem defending his vision against people like Heisenberg. And Heisenberg essentially tore him and Einstein to pieces. Okay, why? Because, Schrodinger couldn't keep up with him. Now here's Schrodinger again, okay? And what he couldn't explain especially was he had a picture, but he couldn't explain the nagging problem, which was the strange instantaneous quantum jumps. His cloud model or his vibrating wave model of energy, he said, well, why does it fall to a lower energy level and rise to a higher energy level? And he couldn't explain that with his equation, with his vision of the atom. Okay, so this is where quantum was at a crisis. And who came to save the day? Well, good old Wernie. Okay, Wernie, Heisenberg, he came up there and he says, oh, I can tell you why. He had this notion. He said he believed it was time to give up a picture of the atom at all, completely. We can't picture the atom, okay? All human attempts to visualize the atom, to model it with familiar images, would always fail. He decided to abandon all pictures of it and describe it using pure mathematics alone. The atom didn't just defy visualization. It even defied traditional mathematics. He came up with these quantum matrix, and he says, this is what the atom looks like. Pure math. So if you want to know exactly what an atom looks like, they're going to tell you to take a course at the university level, because otherwise you won't understand what it looks like. It's like saying, what does a rock look like? Oh, you got to take a course at the university level to know what a rock looks like. Okay, so you go to the university and you say, okay, I want to find out what an atom looks like. This is what an atom looks like. There you have it. It's a little matrix, bunch of equations, a couple square roots, right? Cube roots maybe. You have the irrational number there. So now you know what an atom looks like when you go to the university. Okay, you got to go to the university to find out that it looks like that. That's what you spend 10 years at the university for. Yeah, they have no picture of the atom, and to make things worse, good old Wernie came up with a new idea which just shocked the pants out of everybody, and that was his notion of the uncertainty principle. He says, I know why the atom cannot be visualized. It cannot be visualized because it's inherently unknowable. Okay. And so good old Al-Khalili, he explained, he says, there is a fundamental limit about how much we can know about the subatomic world. That's what Heisey found out about. If we know where an electron is at a particular point in time, then we cannot know how fast it is moving. But if we knew its speed, we would know its position. That's essentially Heisenberg's uncertainty principle, or principle of indeterminacy. Okay, it's a fundamental truth about how nature behaves at the subatomic scale, known as Heisenberg's uncertainty principle. No, it's how nature behaves when you model it with particles, which is irrationally. Okay, the reason this is nonsense is because, and you can try this experiment at home, always in the presence of a trained quantum mechanic. Okay, you put a ball on your table. Do it carefully. Okay, this is a very dangerous, very expensive experiment. Okay, you put a ball on the table and you watch it for a while, and you'll notice that it doesn't move. So you know its position. You know how far it is from the edge of the table, all that. You can even measure and check, and it's always there. So you know its position, but you don't know its speed because it's not moving. Now roll it across the table. Well, now you know that it moves. You can even time it. You know, you can check how fast it's moving. What is its position? Position, location, really, in rational science, location is a static concept, whereas motion, or momentum as they call it, is a dynamic concept. So yeah, the more you know about how a ball moves, the less you know about its location. The more you know about its location, you know nothing about its motion. That's what Heisenberg discovered. He got a Nobel Prize for that idiocy. Okay. And today it's one of the golden rules of quantum mechanics. So please don't laugh at it. Okay. Okay. Here's good old Jimmy gawking at duality. You know, the fact that everything in quantum mechanics is a paradox, among them complementarity, invented by Mr. Niels Bohr, saying that the atom, light is both a particle and a wave. And that goes for everything, essentially, for the electron, I guess the atom, everything behaves as both, a particle and a wave. That way they cover all the bases. It never occurred to them that it could be neither, that maybe it's a rope, light. That's a totally different concept completely, okay? A totally different theory. Atoms are not just unimaginable, they're self-contradictory. I mean, these people are admitting it. They're telling you in your face they're unimaginable, self-contradictory. Then you have all these people out there who are, you know, they just look at these things very superficially, and they say, oh no, they have proven the atom. We wouldn't have computers if it weren't for quantum, blah, 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 blah. Here they're telling you, atoms are not just unimaginable, they're self-contradictory. They behave both like particles and waves. Yeah, no kidding. And it gets weirder. Oh, it does, okay? When you aren't looking at an atom, you're going to need a couple drinks to understand this, okay? So go get your beer, okay? It behaves like a spread out wave. But when you look and to see where it is, it behaves like a particle. This is insane. Yeah, completely. Totally agree. So he did have some good points in his presentation. He said it's insane, it's surrealistic, it's poppycock. That's what he's saying. First, atoms couldn't be visualized at all. Now it seems they change completely in character depending on whether or not you're looking at them. Now, how sick is that? And this supposedly is what all these mathematicians believe in, okay? Okay, so Jimmy continues with his presentation on the atom. He says, look, good old atom man there, okay? And he gawks. He says, it revealed a shocking contradiction at the heart of nature. Everything we see is made of atoms, and yet atoms themselves are unknowable. They can only be understood through mathematics. So if you want to know what a dog looks like, you got to take a course at the university level, because you can't just point and know what a dog looks like. You need to find out, you know, the wave equation of the dog or something. I don't know. The probability wave of a dog to know what a dog is. That's what these people are saying. Okay, and so he continues, he says, the old God was replaced by the new. No kidding. I mean, I preferred the old God, really. The guy with the magic wand, I could understand that. I could see that God, you know. Who is it? Michelangelo, he painted God, so I respect him because now I know what God looks like. He's got a beard, you know, a little magic wand. He's got all these saints and angels around him. The old God was replaced by the new, no doubt. Chance and probability became interwoven into the fabric of nature itself. And we could no longer describe atoms in terms of simple pictures, but only using pure abstract mathematics. Now, how's that for physics? How's that for understanding how the universe works? You got to take a course in mathematics just to know what an atom looks like, because all you can do is put an equation, in this case the matrix that Wernicke invented, okay, and so here we have good old Niels Bohr, and he summarizes for us: everything we call real is made up of things which themselves cannot be regarded as real. Of course, he never defined the word real. He didn't know what the word exist means, because he didn't define that as well, but he talks about what is real and what is not real. But that's his conclusion. It just gives you an idea. These people have no clue about quantum, which is how they pretend to describe the atom. And they can't describe it except mathematically. And I mean, they can't point to it. They can't give you a picture, a drawing of the atom. Is an atom, but they say that an atom is what caused the pollen, you know, Brownian motion, would cause the Brownian motion to occur, to the pollen to move. They say it's got to be something, but now they have that something, and they say, well, but you cannot even visualize it. You're not allowed to. You can only approach it through mathematics. Solvay 1927. This is another gawking moment of Al-Khalili. He says Solvay 1927 that's when the conference took place in Belgium. Was the turning point at which the rest of science establishment came to embrace the Copenhagen interpretation, and that interpretation is still accepted today. That means today the Copenhagen interpretation of quantum mechanics is the authoritative one. It's the party line, okay? And what do they say? You cannot visualize, you cannot even imagine the atom. Don't try. If you do, we're going to call you a heretic. We're going to say you're a crank, a crackpot. So don't even try. If you draw the atom, you're going to be kicked out of quantum mechanics. You're not supposed to draw it. You're supposed to express it in matrix form. Okay? You got to put all those square roots, numbers, then you're okay. But don't try under no circumstances to draw and illustrate the atom, because it's you cannot even visualize it. Whatever you draw is wrong. That's the Copenhagen interpretation. Okay, all the physicists that I used, all the physics that I use, this is Al-Khalili giving us his testimony. Okay, all the physics that I use in my research, certainly the quantum mechanics that I teach my students. This is how these things get rolled by from generation to generation. Okay, passed on down. And that fills the textbooks on my shelves is based on ideas that were hammered out and crystallized here at the Solvay conference in October 1927. In a sense, everything I know about the way the world around me is made up started here. Over the last 80 years, it has been proven right time after time, and its authority has never been in doubt. Now, how's that for a statement of religion? Is quantum mechanics a religion or what? I mean, these people just learn it by rote. They repeat it because it was handed down by the great white fathers of quantum mechanics. They're not willing to challenge it, partly because they would be kicked out of quantum mechanics, meaning they will not get a job, a career. So they have to fall in line. Those people who are smart and they say, well, you know, I can't take this any longer, they drop out and become engineers, lawyers, doctors, whatever. But those who stay, they have to repeat the catechism. They have to know it by heart. And that's where good old Jimmy falls in. That's why I have little respect for him. All he did was memorize what the forefathers told him, and that's it. He just repeats it now on TV. That's all it is. Okay. A couple more things here. Here's, they say you can't picture the atom, you can't picture the electron. Here's a Swedish team, and they took pictures of the electron. and they made this movie by taking snapshots, many snapshots, and they explain how they did it. You can look it up, but this is their result. They say that's what an electron looks like, a little ball that goes around the atom. Okay, and so on the one hand, you have the quantum guys saying you cannot even imagine the atom, let alone the electron. These people are saying, oh, we filmed it. So now, what are we supposed to think? I mean, are these guys idiots or what? All of them, because they don't even know what the other guy is saying. We don't even know what the catechism is anymore. I mean, are we supposed to imagine, visualize the atom, or are we not? These people are saying we filmed it. These other people say, no, you can only get it through a little matrix, a little mathematics there. What are we supposed to believe now? What are you supposed to, what is quantum mechanics? What is the theory? Okay. Okay, so what is that these people missed all these years? Well, here you have the rope model, okay? Two-dimensional, three-dimensional rope model of the atom, very simple. And so yes, we can visualize. We had better visualize it if it's a physical object, okay? And are we supposed to visualize or imagine or watch the quantum jumping? Here it is. Here's the quantum jumping in 2D, but you can understand what's happening there. The atom expands and contracts. By doing so, it torques the rope. That's it. That's quantum jump. That's how difficult it was all these years. All we had to do was make a new assumption about, the atom and how it really works. Okay, so getting here the final part. One more time, I'll go through the conclusions. My conclusions, in other words, the fatal flaws I want to point out in Al-Khalili's argument. First, he argues that he learned physics by rote. Okay, essentially that's what he's saying. He just gawks at the forefathers that he had that gave him all this information. He calls them giants, but he's Atom Man, so I guess if he stood on the shoulders of these giants, they were maybe pygmies. I don't know, dwarves. The conclusion of these mental midgets is that the Copenhagen interpretation of QM, which says, essentially states that you cannot even visualize the atom, so don't even try. Okay, even though here you have these people in Sweden that they filmed the atom, so they do a little more than just visualize, they filmed it. Okay, they claim that they filmed it, and you'll find a lot of people who say they took pictures of the atom as well. Okay, so I don't know what all these people are talking about. And the only way to approach it through mathematical description. The mathematicians refer to this description as a theory. It's not a theory because a theory is an explanation. Quantum can only describe, okay? So there is no such thing as quantum theory. And the result is that everyone anyways just uses the planetary model to do, electricity and ionization and collisions. They use that model anyways. So by default, that is the quantum atom, except that they'll always deny it at the end of their presentations. And just like with gravity, they cannot explain why the electron bead does not leave this solar system planetary model. Okay, so there you have it in a nutshell. What should you think about Al-Khalili? Well, not much about him. He didn't make a very good case. He started saying that they explained everything. It turns out they explained nothing. They don't have any explanation, any rational explanations, which means they do not have an explanation. For that matter, I can just go with the explanation we had 1,000 years ago. Angels move the earth around the sun. That's a good explanation. Why not? I mean, better than this one. At least I can visualize angels going around the sun, pushing the earth. Okay, I can also visualize angels on two magnets holding hands and attracting each other. I can do better than quantum just by postulating angels. So maybe my angel theory is a little superior to quantum mechanics, because this one they tell you can't visualize it, don't try to imagine it, because you can't. The only way to approach it is go to the university, learn a bunch of math, and then you'll understand. You know what I mean? Anyways, with that, I'm going to see you on Wednesday, and I'm going to continue with Al-Khalili, because he's got a lot of material out there, and it needs to be debunked. It needs to be brought to light what these guys are passing on down, not only to his students, to people that he teaches directly, but also to the new generations who, just come in and they want to get some information on quantum mechanics and general relativity, and they come in and they just get bits and pieces and say, oh, okay, so that's what we've discovered, huh? So we need to, for those few people who stay a little longer and they are really critical, they will find that there's a lot to criticize in mathematical physics. None of it survives. None of it survives. We'll see you on Wednesday. We'll see you.